This is the second hour of Physics 1B for December 6th. And the next thing we're going to be talking about are perceptions of sound waves. Okay, so when we hear sound, we hear different things. We hear things like how loud it is, right? So one of the features of sound is how loud does it sound? How does this correspond to the physics of what we just described? Well, since sound's a pressure wave, this is going to correspond to large values of delta P max or of A, either one. When the change in pressure is large relative to atmospheric pressure, then the sound is going to sound louder. So when you turn the volume up on a device, that means you're basically just making it so that the pressure variations are going to increase while keeping things like the frequency the same. We'll also hear things like pitch. Pitch is like something that can be really high-pitched or something that can be really low-pitched. And that corresponds in sound to frequency. I believe we probably talked about this at some point in this class. Probably last week when we were talking about standing waves, right? Now, when something like an instrument produces sound, one thing we'd like to know is kind of what does that look like? And over here, somewhere, right here, we have a waveform produced by a clarinet and a waveform produced by a recorder. Recorder is just a really simple type of wind instrument. So let's look at these two waveforms. What's plotted here is pressure as a function of time in both cases. Different instruments. The instrument over here is a clarinet, and here's the person playing the clarinet. And this is pressure fluctuation versus time for a clarinet with a fundamental frequency F1 equal to this. If you hook up a clarinet and play it in front of a speaker, you can get all kinds of various programs to produce this waveform for you here. Now what you might notice almost immediately is it doesn't look like a sine wave anymore, right? Over here, with the recorder, which is a simpler instrument that produces less rich sound, the frequency does appear to be such that, or the waveform does appear to look a lot like a sine wave. It's not quite a sine wave though, right? Can you all see that this one's a little bit different than a sine wave? Like, it's like a tilted sine wave, right? Can you see how this slope is not the same as this slope? I didn't notice this earlier. See, look at this slope on the upslope and compare it to the downslope here. Can you see the upslope is much less, well, much steeper than the downslope?
Yeah, I can see that.
You can see that, right? Okay.
Very slight, you're right.
It's really small, but it's important because it's not a pure sine wave. It's actually a combination. It's a combination of multiple sine waves that have been added together. And one of the cool things that you can do, let's go back to the clarinet here. We can say, man, that's a really complicated signal, right? Is there any way I can look at that in a simpler way that I can understand? And there is. So this is a periodic wave. The waveform is just kind of strange, but it does repeat itself. You can look at the portion here that's below the axis and the portion here that's below the axis. They have exactly the same waveform. And you can compare like this portion here to this portion here. So it's producing a uniform wave function, you could say, of pressure versus time. But what we can do is to go from the upper picture to the lower picture, we can use something that's called Fourier analysis. And what it does is it effectively breaks our more complicated wave down into its, almost like its elements or its components, which in this case are going to be different individual frequencies. So now we have a new plot that plots the amplitude of the sound to the frequency that's producing it. And in this case, it's a fundamental frequency of 233 hertz, but included within that, this would be 233 hertz right here. That's F1. But it appears to also have some 3 times that frequency, some at about 6 times that frequency, a little bit at like 7 times that frequency, and the combination of all of these together produces what we think of as that clarinet sound, which is going to be a lot more full compared to the recorder, which when we do the Fourier analysis to go from here to here, we can see that this particular wave is only composed of waves that are mostly with the fundamental frequency and F2. It's just those two. So really what you have to do to produce this wave is you need to have a wave that has a lot of F1 and a wave that has a little bit of F2. And when you add those two together, you get this wave, basically, right? One way we could think about that is that something like this. If we do pressure of x and t and say that it's a sum, based on the way that I'm looking at this here, of a1 times the, what we're using, cosine of kx minus omega t, we'll call this omega 1, probably k1, plus a2 cosine of kx minus omega t as well, we'll call this k2 and omega 2. I believe, if I understand correctly, that this is what the wave is, where, omega 1 is 2 pi f1, and omega 2 is going to be 2 pi f2. And you could also figure out what k1 and k2 are. You would just need speed, right? Because k is equal to 2 pi f over velocity, right? So k1 would be 2 pi f1 over v, and then k2 would be the same, right? So when we do Fourier analysis, what that allows us to do is to say that really this upper wave right here is just a sum of two different cosine waves. Now, I'm leaving out a little bit of details here because if you look carefully here, there's also a contribution at F3, F4, F5, and F6, right? So you'd also have to have a plus ... here, where you're going to have A3 times the cosine of K. You get the idea? You just continue on, and basically you can construct any function, not just waves. You can construct any function you want as a series of cosine and sine functions. Did you all know that? That you could take any function you want. You could take y equal to x squared, and you could write a series of cosine and sine functions that will approximate like y equal to x squared. Have you all learned about that in your math classes yet? About this idea of Fourier analysis? Where you can have multiple waves that add together to produce a function? Maybe not, right? But you've probably learned about like Taylor series and Maclaurin series.
Oh, yes.
And the Maclaurin series, what do? You basically say that give me any function and I can give you a series, a polynomial series that reproduces that function, right? That's what a Taylor series is, right? What a Fourier series is the same idea, but instead of making a function out of polynomials, you make a function out of sine and cosine waves, and it works just the same. It's really powerful. It shows up a lot in physics. I know it showed up quite a bit in the physics I did with particle physics, where we were talking about extra dimensions, and this is one of the things that showed up as well. So, other things that, we'll talk more about this, but other things that that show up when we're talking about music, there's this thing that's called timbre. This came up last week, timbre, when we were talking about overtones. So remember last time we talked about fundamental frequency, and then we said that these things, the higher frequencies, are like what are called overtones. And the effect when you play a musical instrument that has a whole lot of overtones, like the clarinet here is, you would say it has a lot of timbre. Timbre doesn't have a specific like connection to, the way that loudness is like pressure and pitch is like frequency. Timbre is more related to kind of the number of overtones present. I think that's the way to put it. I'm probably wrong, though. Does that sound right, Kate? And when there's less overtones, it's going to just sound like a single note. That's going to be kind of weird. Now, how does this work? How can you have all of these different frequencies coming together and it doesn't sound like just garbage? Well, the way that works, let's see if I still have this pulled up here, is if I have this virtual piano, I'm pretty sure that I need to change the screen or else you won't be able to hear this. So we're going to go change windows to this virtual piano. Okay. Can you all see that, or can you all hear that?
Yeah, we can.
Yep.
Okay. Apparently you can download this on Android and stuff if you want to. Okay, so what we're going to do here is we're going to look at this key right here, which has a dot on it. I think this is supposed to be middle C. And we can click it and hear how it sounds. Now, this already isn't just a pure note. You might be able to tell. It sounds like a real piano, actually. That's really what a piano normally would sound like. And you're hearing lots of different frequencies, okay? Now, what we can do is we can say, if this is middle C, it corresponds to a frequency of exactly 256 hertz, okay? If I then go to the next C, and you can see C on a key, I don't know how many of you have played a piano before, but you've got these 2 and then 3 of the black keys, right? So there's 2 black keys here and then 3 black keys, and there's a gap where there is no black key here and there's no black key here, right? The black keys occur every half key, right? Directly to the left where you have the 2 keys, so like where the 9 and the 0 are here, this is C, and then this is C again, and this is C again, and this down here is a lower C. And then the letters just go up from there. So this is C, D, E, F, G, B, A, C, and it repeats itself. There's a total of 8 notes. Now, when you play 2 notes that are 1 octave apart from each other, we say that this key here is 1 octave above this key here, then the frequency is exactly double the frequency. So if this is 256 hertz, double 256 is 512 hertz, which is this here. Higher frequency, so it's higher pitch. And you can hear, going from here to here, the pitch is higher. So what happens when you push them together? When you push them together, it sounds like this. And when you push them apart, it sounds like this. And then together. Do you notice that when you play them at the same time, it still sounds like exactly the same note, but it just kind of sounds more full now? Can you tell the difference? So that's what we mean by timbre. There's more timbre here than there is here. Now, why does it sound good and not bad? When you play 2 notes at the same time, it could sound really bad. But in this case, they sound pretty good when you play them together. In fact, it almost just sounds like you're playing 1 note, right? Well, when you play 2 sounds that have similar frequencies, that is to say whole number multiples of frequencies, then they don't interfere with each other. They really just kind of boost the sound, right? Because these 2 waves basically overlap each other every half cycle, or every 2 cycles. Should I draw that, or is that obvious to you all? You won't be able to see anything I draw, so I'm going to stay on here for just a second. We'll go back and draw in a second. Okay, so we call this, I think this is called consonance, right? When you have 2 sounds that don't sound bad when you push them at the same time. But if I play 2 notes that are right next to each other, like this one and this one, if I play them at the same time, it produces what's called dissonance, because there's a lot of interference between the sounds. So let's push these 2 together. Would you all agree that kind of sounds bad?
Yeah, it's pretty bad.
It doesn't sound good, right? But if I separate it by 2 notes, suddenly it starts to sound good again, right? And then if you play, what is it, IPX, playing all these together, this is what we call a chord. And it's kind of at the core of how most modern music is produced, is through chords. Anyway, but the main point to take away is that what's being shown here. Okay, I'm going to switch back to sharing screens of my OneNote. So basically what's being said here is that this complicated wave function here, right, is made up of a whole different bunch of pieces, right, that are all like playing a whole bunch of notes on a piano that are all separated out by an octave. That's pretty much what this is saying. But there's like different proportions. It's like a weighted difference. Most of what you're hearing occurs at the fundamental frequency, some at 3 times the fundamental frequency, some at 5 times the fundamental frequency, and so on and so forth. But this basically creates this wave. Okay. Now, another thing we can do, I didn't mess with this in my other class, but we have a little bit of extra time here, so we're going to try to do this. So this is on the FET website. It's called Fourier Making Waves. What is this one? That's probably too much. Let's start with this one right here. Okay, so this has the same amplitude versus x, amplitude versus x. How does this work? So here what we have is, yeah, that's what I thought. We can basically add and subtract different pieces of our wave, right? So you've got these different amplitudes here. See, I would think it would be in frequency space, function of space, space and time. Oh, we can make a move. That's kind of cool. Equation. This is not exactly the same thing, is it? It's not exactly the same thing. But well, we can kind of figure it out. So let's look at this one here. So what did we have? This one had a healthy dosage of F1 and a healthy dosage of F2 and a couple other things here. Let's see if the new Fourier thing is actually going to look like that. So we need to add in a little bit of this. And some more of these too. So maybe just a little bit of here, a little bit here. And now we have a new waveform. Can you see how, so here they have the different waves that you're adding together. And this is what the new wave looks like down here. So that's kind of what's going on. And this does kind of look a little bit like this wave in the sense that it looks like a sine wave, but it's not quite a sine wave, right? Anyway, infinite harmonics, that's not going to let us do that. I don't know how useful this is, but the point is that you can make any function you want through a combination of a bunch of waves. You can start to get really weird. Something like this. Anyway. Okay, let's keep going. Anyone have any questions or comments? All right. The last topic for tonight is the speed of sound in different materials. We got a couple problems we can do with this. Oh, that's nice. I cut it and then it repasted it way over there. Come over here, click here, paste. Boom. All right. I won't move all these. Move this one down here. Move this one down here. Okay. So let's talk about the speed of sound in various materials. First of all, speed of sound in a fluid. Oh, no, all right, okay. I mentioned that. All right, speed of sound in a fluid. Okay, when we talked about the speed of waves on strings, one of the things I mentioned was that in general, when you find the velocity of a wave, it's always going to involve some kind of a restoring force in the numerator and some type of a inertial force or just inertia in the denominator, okay? As an example, when we had a string that had a wave on it, we said that the velocity was equal to the square root of the tension force divided by the mass density mu, right? So the restoring force is the tension, the tighter it is, the faster it's going to go, and the density shows up here down at the bottom. So in a fluid, what we're going to get is that the velocity of the wave is going to be, our restoring force is now going to be the bulk modulus, and the inertial force in the denominator is now just going to be the normal density. So that's going to give us our velocity of sound in a fluid. We can also find the speed of sound in a solid by using the Young's modulus. So for the speed of sound in a solid, we're going to get V is equal to the square root of the Young's modulus, also I think divided by rho. So using these ideas, you can produce a table like this one over here. So let's look at the liquids and the solids right here. So in air, we've got velocity of about 344 meters per second. But when we look at helium, for example, right here, helium, the velocity is only 211 meters per second. So what does that mean? Oh, whoops, that's liquid helium, sorry. I was like, that doesn't make sense. Helium at 20 degrees Celsius has a speed of almost 1,000 meters per second. And you know that if you inhale helium, it makes your voice sound really high-pitched, right? Let's see if we can understand why that's the case. So since velocity is equal to wavelength times frequency, that means that frequency is equal to velocity divided by wavelength. Yep. So if the wavelength remains unchanged, which would be reasonable if you're speaking, but the velocity does, then the frequency is going to be higher, right? So things that have, like helium, that have higher speed of sound, your voice is going to sound even higher. I'm sure it's not safe at all to inhale hydrogen, but if you were to do so, your voice would sound even higher, maybe even so high that it wouldn't even be audible. I don't really know. because our ears are only sensitive up to about 20,000 hertz or so. All right, so that's why it is that your voice sounds really high with helium, and yeah, I don't know what else to say about it. Sound can propagate through these other materials as well. It looks to me as though the velocity of sound through things like solids are much higher than the velocity of sound through these liquids. So that means that, suppose you have a long metal bar, like let's say a train track. Let's say you have some train tracks here, right? So here's some train tracks. And let's say they're made of iron. So this piece right here is iron. And then these are just ties, like the railroad ties. Now let's say that you're sitting over here and you're laying down on the track. Maybe you're listening for oncoming trains or something like that. So you've got your ear right here on the track, right? And let's say you have a friend over here that's really far away, and they take a hammer, right? And they bang on the track, okay? So they bang on the track here. What are you going to hear first? Are you going to hear first the vibration of the sound coming along the iron, or the vibration of the sound that propagates through the air? Which would you hear first?
I'm assuming through the iron.
The iron, right? I guess iron's not listed over here, but you can see that all of these have significantly higher velocities than the air, right? I guess I could have chosen steel, so we'll make it steel. Just, that would have been better, I guess. But you're right, Andrew's right, that you would hear the vibration in the steel before you heard the vibration through the air. Now, at the same time, they're both really fast, right? 344 meters per second. You're probably going to hear them around the same time, but if you could somehow figure out a way to, maybe if you get really far away, like maybe if you're a few miles away or something like that, it may be a bigger effect, right? Because I think even if you're a mile or two away from someone banging on a piece of steel, you're going to hear that, right? Wouldn't you think? Metal on metal, that's pretty loud, right? And if they just keep banging it over and over and over and over again, you would definitely hear a delay between when you hear the sound through the air versus the pulses that you would be hearing through the steel, right? Does that seem reasonable?
Yes.
Okay, one final thing before we do these two problems. The speed of sound in a gas. So they say that in a gas, the buoyant force is equal to gamma. We know what gamma is for a gas, right? Gamma, if you remember, is it CP over CV? I think that's what it is, right? CP is always greater than CV. I mean, I got that. But it's the ratio of the molar heat capacities. If you multiply gamma times the pressure at which you've if you multiply gamma times the pressure of the gas, then this gives you the buoyant force. I didn't try to derive this earlier, but maybe we can try. Maybe we know enough to actually derive this now. I don't really know. We said from above, the velocity in a fluid was B over rho, right? Buoyant force divided by density. If we plug in is there a way to derive this? They don't actually show it, but maybe we know enough to derive it? $16.7. Okay, well, that doesn't help. What is P equal to? For a gas, pressure times volume is equal to nRT. So, and density is what? Mass over volume? So this is like gamma P naught mass volume. Oh, this is easy to derive. So this is going to be equal to the square root of gamma RT. PV is going to be equal to nRT, so there's an N here as well, divided by mass. But if I take mass over number of moles, what's that equal to? If I take mass and I divide by number of moles, that's a fixed number that we know about, right? Do you all remember? I give you a mass of a gas, like it's 1 kilogram, and I say that it has 2 moles. I take 1 kilogram, I divide by 2 moles, I get 0.5 kilograms per mole. What is that? Anyone remember? You take the mass, divide by number of moles. It's going to be molar mass. Yep, this is molar mass. Molar mass, which is m. So that means the velocity for a gas we can find by just doing gamma times r times t and dividing by the molar mass. So this is the chapter we're doing right now is chapter 17 or something like that, 16. And of course, these topics don't occur in your textbook until like chapter 18 and 19. So since we've already done those, it's kind of nice we can actually figure that out. All right, we're going to do 2 problems here, and that'll be all for tonight, I think. Oh wow, we're going so much faster than we did this morning. When I had class this morning, we spent, I believe we spent an hour right here trying to understand this part. We spent like an hour trying to figure this out. Anyway, so here's our problem. A ship uses a sonar system to locate underwater objects. Find the speed of sound waves in water using equation 16.7 and find the wavelength of a 262 hertz wave. All right, so I put up here what the bulk modulus was. That's the bulk modulus for water. And to find the velocity of sound in water, we just need to take the square root of b and divide by rho. But rho is the density. So in the numerator, we'll have 2.18 times 10 to the 9 pascals. And the denominator will have density, which is, for water, is 1,000 kg over meter cubed. And I'm thinking about what we were talking about earlier. I'm really wondering when you learn about Fourier analysis. Like, you have to learn about it at some point, right? I say that. Maybe you don't. I don't really know. It might not be until you're, like, junior, senior level of classes. I don't really know. I think I didn't learn.
I don't know, because I know I've heard about it, but you learn about Taylor series, Maclaurin series, and Power series in Calc 2.
That's Calc 2?
You don't really learn anything, any other series in any other topics.
Okay. Can you see how they're basically the same thing, though? It's like, with Taylor series, you're trying to compose something out of polynomials. With a Fourier series, you're just trying to do the same thing with sine functions.
Yeah. You just add a bunch of them.
Yeah.
Equivalent line.
Mm-hmm. I think I first learned about it in, I guess it was quantum mechanics. So you know what? You probably learned about it in Physics 1D, actually. I mean, I haven't taught 1D, but you probably do learn about it in Physics 1D. So it might come up again. Because, well, not to spoil anything, but it turns out that the way that all matter works is on these things called wave functions that are that behave a lot like this wave stuff we're learning here. In fact, what we're learning right now with all these wave properties is directly related to stuff you'll learn in 1D when we start talking about elementary particles and stuff and how they behave.
I'm pretty sure you can probably. I know this is probably like a bit extreme, but
What?
if frequency was a bit too high, you can probably kill somebody, huh?
I don't know about killing someone. You can definitely produce a huge amount of pain and I think break their eardrums, causing them to bleed. I think.
I don't know why I was thinking that, but
No, it's a really good point. We should always be thinking about death. It's important. But there's what we call a threshold of pain. We're going to talk about it here in a little bit, but you can imagine that if you go to the airport, right, and you stand right next to where the planes are taking off, right, and you hear all these planes taking off, that it's going to cause some serious damage to your ears, right? Also, if you just go to way too many concerts that are really loud, like let's say you go to a bunch of heavy metal concerts and you sit right next to the stadium and you don't use earplugs, you can cause a lot of damage to your ears for sure. Whether you can kill someone, I mean, I'm sure that if the sound has a high enough intensity, so if the loudness is really high, right, and then you'd want to have really high frequency because really high frequency is going to be really high energy as well. I think it's conceivable that you could kill someone. I don't know though. I'll let you work on that in your mad scientist laboratory. In a few years.
Thank you.
Yeah, no problem.
How loud are gunshots? Like,
They're really loud, man.
comparatively?
They're
Because I
really
know
good.
they're really loud. I've heard them, but at the same time, it's like you watch videos and they're like, or you watch movies, they're just shooting guns
Oh,
without anything, and you're like, wait,
yeah. That's
that thing, their eardrums are probably dead.
yeah. All the people in those movies like can't hear anything. Yeah, exactly. They'll be like shooting guns around kids and stuff too, and you're just like, all right. Have you uh have any of you ever been to a firing range where you can just go shoot guns?
Yeah, yeah,
Yeah.
Yeah, and you always have to wear like big protective ear equipment. They kind of look like these too, actually, right?
yeah.
Really, really
Really,
big.
like
And even when you put those on, it's still really loud. In my memory, at least when you shoot. Like I went to a place in Vegas to shoot like automatic weapons, and oh my god, those things are so loud. Like shooting semi-automatic and automatic weapons, they are incredibly loud. My understanding is if I was to be sitting here and someone was even in the same room as me and they fired a gun, I'm pretty sure that I would temporarily go deaf for a few minutes. I think so. Guns are extremely loud, really, really loud.
I know I don't know if you watch comedy, but Bill Burr has a
Mm-hmm.
stand-up special where he like wants to buy a gun, and then he talks about that. That is like, I'm gonna go deaf.
I like that. Bill Burr is amazing. I love Bill Burr.
It's my favorite.
Yeah, I have to go look for that. I may have heard that actually too. That sounds familiar. Okay, let's talk about speed of sound in air. So this says, find the speed of sound in air at t equal to 20 degrees Celsius, and find the range of wavelengths in air which the human ear, which can hear frequencies in the range of 20 to 20,000 hertz, is sensitive. The mean molar mass for air, m, is 28.8. And the gamma quantity is 1.4. We're all pretty familiar with this. And we're just trying to figure out what the velocity is, so we can use the equation that we just derived, which was square root of gamma RT over molar mass. So we've got gamma is 1.4, R is 8.31, and then T, temperature. This has to be absolute temperature, so for 20 degrees Celsius, we're going to kick that up to 293 Kelvin. And then divide by molar mass, which is 28.8. And then we just got to root all that. We get V equals. But yeah, absolutely. In movies, when people are shooting each other and there's just like absolutely no ear protection, you know, people would definitely go deaf. Some movies are realistic about it, though, right? Some movies you do see people like shooting guns, and then you see physical harm occur. Like I remember, I was watching I think it was called Boardwalk Empire, some show on HBO a long time ago, and in the show there's a character named Al Capone. And he walks up to someone in a bed and he puts a gun into the pillow and shoots the gun in the pillow. And the person obviously hears that. They wake up and their ear starts bleeding. Like some movies do a good job of it. But other movies, they're just like, people shoot guns and there's just no effect. It's very unrealistic. Well, that's pretty much all that I had planned for today. That's what we got through in the morning class. But I guess we could go just a little bit further here and talk about sound intensity and the decibel scale, maybe. Let's see if we can do that. I didn't actually even read ahead for this part here, but we can probably, we've got enough time left. We might as well not waste it because we're going to have one last meeting next time. So let's talk about sound intensity. All right, how are they going to do this? So they're saying that what we're going to do is pressure times velocity. Why would pressure times velocity be intensity? Huh. Let's think about this. So they're saying that if I take the pressure as a function of x in time, which we know, which was, it was like BKA, it's sine omega t, sine of kx minus omega t, right? That was our pressure function, right?
Yeah, it was.
And if we take our velocity function, the velocity function of x and t was pretty similar to this, but it was just the ka sine of kx minus omega t, right? Oh, no, we didn't actually do this. We did del y del x. Sorry. The velocity function should be del s del t, which is going to be, since s of x and t was equal to a cosine of kx minus omega t, then del s del t would be negative sine of kx minus omega t. And then we would pull the negative omega out here, and we'd have a times omega, and that negative would cancel out from the fact that when you go from cosine to sine, you get a negative sign. What they're saying is that we can say that intensity of a wave, which is normally thought of as basically power over area. I mean, that's how we said it before. It was power over 4 pi r squared, right? They're saying this is equivalent to pressure times volume. Not volume, velocity. Pressure times velocity. Is that really what they're saying? Let me read this real carefully here. Oh. So power, here's how we do it. So power is equal to force times velocity. Well, really dot product, but force velocity. So if I want the power over area, right, to get intensity, so if I divide both sides by area, well, force over area is pressure times velocity. Okay, it makes sense. It actually makes sense. Okay. So if intensity is pressure times velocity, then our intensity I for a wave should be BKA. That's our pressure times this. Or written together, that is BK omega a squared sine squared of kx minus omega t. And now I'm pretty sure what we're going to do is we're going to time average this. We're going to average this function over one period. It's probably just going to give us a half. We've done this in this class before, but when I have something like a sine squared or a cosine squared function, if you time average it over one period, this whole thing is just going to be 1/2. And we've done that before in this class. This is going to give us the average intensity. And that's it, I think. Oh, and then we can replace... What do we want to do? We want to throw velocity in here or something? Omega equals v times k, and v equals, okay. So we're going to use omega is equal to v times k, and we're going to use the fact that v is equal to the square root of b over rho. And then, are we eliminating the b? What are we eliminating? I don't know. Let's just go through the steps and we'll figure it out. Sometimes I don't immediately see how they're doing things. We want to leave the b in here. We put the 1/2 in the front. It looks like we do want to get rid of k. So k is going to be equal to omega over v from that equation. And we have an omega here as well. And we have our a squared. And now let's replace velocity. So 1 over velocity is going to be the square root of rho over b. So then this is going to be 1/2 b omega squared a squared. And we have square root. So 1 over v is the square root of rho over b. So we have the square root of rho over b. And then we can say that the average intensity of a sound wave is going to be 1/2. So b over root b is just going to be square root b. So we're going to have the square root of rho times b. Just that part is square rooted. Times omega squared times the amplitude squared. And that's going to be our average intensity for our sound wave. I think we had something similar in the chapter on... in this same chapter? No, the last chapter on mechanical waves. So that's our average intensity. Or they also give this other relationship, which is the intensity is equal to P max squared divided by 2 square root of rho times b. And I believe this is probably pretty easy to go from here to here if you just say that P max is equal to kBA. You should be able to easily prove that this one turns into this one. I can see it pretty easily. I'll let you all do that yourself if you want to. So 2 different relationships, depending on what you know. This first one, I mean, both of these contain something that's kind of hidden, right? Maximum pressure is the maximum pressure fluctuations that occur within the air. This is very hard to know. And then the amplitude A is also very hard to know. I think quite often that's going to have to be given to you in a problem. The rest of the quantities are pretty easy to look up, though. The frequency is going to be something, you're going to know frequency. Density and bulk modulus can also be looked up. Okay, so let's do one of these problems. Oh yeah, we've got plenty of time. So I'm just gonna go ahead and pull up the problem and copy paste it in here. So we are on sound intensity, and here are the problems we want to do. So let's do this one first. This is going to be a very plug and chug kind of problem. Okay, I'll leave the formulas up here. It says find the intensity of a sound wave in example 16.1, where we had P max was equal to 3 times 10 to the minus 2 pascals. The temperature is 20 degrees Celsius, so that the density is 1.2. And we'll use speed of sound equal to 344 meters per second. We're also going to need to know the bulk modulus of air, which is, it was something times 10 to the 5. I think it was 1.42 times 10 to the 5 pascals. I love how they put all the information on here, but they don't put this one. I don't know why. What else do we need to know? That's all we need, because it tells us that the intensity then is going to be P max squared, which is 3 times 10 to the negative 2 pascals. Those are the pressure variations. We're squaring that, and then we divide that by 2 times the square root of the density, which is 1.2 kilogram over meter cubed, and then multiply that times bulk modulus. You continue to make sure that I'm using the right bulk modulus. Oh, they're not even doing it that way. They're using another version of this equation. They're using this version of this equation where you get P max over 2 rho V. Okay, well, we'll do it this way and see if we get the same answer. Okay, so using those numbers, we get 3e minus 2 squared divided by 2 divided by square root of 1.2 times (1.09 times c). I get the same thing. So we get 1.1 times 10 to the negative 6 watts over meters squared. And that is one way to measure intensity. But the reality is that we don't usually measure intensity in this unit right here. We usually measure sound intensity using decibels. So let's talk about the decibel scale. There's a couple other problems we can do here, but I want to make sure that we get this covered today. So the way that the decibel scale works is, let's see if I can remember this off the top of my head. No, I don't think I can. Can I? Pretty much what we do with the decibel scale is we say that we measure the intensity relative to a specific intensity. So I believe what we do is we say that the log, you do 10 times the log of the intensity of your sound divided by a reference intensity, which is I naught, and I think I naught is it 1,000 or is it 10 watts per meter squared? I can't remember. I'm gonna have to look at the book. I just off the top of my head, I don't remember how this equation works. It's 10 to the negative 12. Okay, I wasn't even close. I knew it was 10 something. So I'll rewrite this so it's more clear. I got the equation right though. So I naught is equal to 10 to the minus 12 watts per meter squared. This is going to be kind of our reference intensity. Reference intensity. And then we're going to construct a scale that looks like this. And the way that the scale works is we measure our intensity and then we multiply by 10 decibels. And that's going to give us, I think they use the symbol beta for this. And this is going to give us decibels. All right. And the advantage of this is that the way that sound intensity works is that the sound intensities that you normally hear happen over a very, very wide range of frequencies. And I'll show you here in the book what that looks like. And we'll do some of these calculations. So over here on the left, what we have is the source or description of the sound. And over here on the right, what we have here, you know what I'm going to do? We're going to go ahead and put this into the thing because it's pretty useful to just be able to do that. All right, let's look at that equation and let's look at this thing and let's see if we can understand how this works. Okay, I like this because it actually has things that we can understand over here on the left. Okay, so down at the bottom here, we have the threshold of hearing at 1,000 hertz, which is an intensity of 10 to the negative 12. This is the threshold of hearing. You'll notice if you go one step up, you have the rustle of leaves. So whatever the threshold of hearing is, it's less than the sound of rustling leaves. And rustling leaves would just be like leaves barely moving around on the ground due to wind or something like that, right? Now, watch what happens if we plug in the intensity level over here on the right, and let's make sure we actually get the decibel level that they show right here, okay? So if I want to find beta for 10 to the negative 12, what I have to do is put 10 decibels here, multiply by the log of, in the numerator you put 10 to the negative 12, in the denominator you put 10 to the negative 12, but the log of 1, right, the log of 1 is equal to 0 because 10 to the 0 power is equal to 1. So that means that this gives us a beta value of 0, okay? So decibels can be negative too, right? Because if the numerator here was 10 to the negative 11, then this would have been the log of 0.1, which I think is equal to negative 1, right? The log of 0.1 is negative 1. Yeah. So you can actually have negative decibels too. So just keep that in mind. As we go up the list here, when I have an intensity level of 10 to the negative 11 watts per meter squared, that gives me a decibel level of about 10. The average whisper is at 20, and that corresponds to an intensity level of 10 to the negative 10. Let's check this one right here, just so we can kind of understand what we're doing. A quiet radio being listened to in your home would be about 40 decibels, which corresponds to 10 to the negative 8 watts per meter squared. Let's see if that makes sense. If I put beta equal to 10 decibels, then I put in here the log of 10 to the minus 8 divided by 10 to the minus 12. Then we have the log of this, which I think is just going to be negative 4. Or sorry, positive 4, right? So this whole thing is going to be 4 times 10, so you get 40 decibels. Does that make sense? It's a little bit kind of a different kind of scale, but do you all understand how how the calculations are done? Or did I go too fast? Did I lose you?
Everything good?
It makes sense? Okay, all right. This is kind of simple. So I don't know. Sometimes things can be simple, but okay, let's kind of go up this scale right here, and then I'll ask you some questions so we can see how well we understand this. So quiet automobile, about 50 decibels. Ordinary conversation, 65 decibels. And we go on up the list here. Eventually, we get to a military jet aircraft at a distance of 30 meters. This is really far away. Remember that sound falls off as 1 over 4 pi r squared, right? So at 30 meters away, what's 1 over 1 divided by 4 divided by pi divided by 30 twice? You get 8.8 times 10 to the negative 5. So at a distance of 30 meters, this sounds about roughly 10,000 times, no, 100,000 times less intense as it would if you were 1 meter away. So if you're looking for the kind of sound that might kill someone, this might actually do it. Anyway, at a distance of 30 meters, it has a decibel level of 140, and this would definitely hurt your ears right here, because it's above this number right here, which is the threshold of pain. This is when you start to feel pain, is at 120 decibels. So you never, anytime you're working anywhere where you are exposed to something like this, you want to make sure you're using earplugs. And as an example, a riveter, I think a riveter is kind of like a jackhammer, isn't it? So give you some kind of idea about these decibel levels here. So here's the first question we can ask about this. Suppose that I have a machine, okay? And I'm in some kind of machine shop. So I've got a machine right here. And let's say it's a really loud machine. Let's say it's producing like maybe 70 decibels. Let's say this machine is producing 70 decibels of sound intensity, okay? So my question would be, suppose I have another machine that's exactly identical in a machine shop or something, and this one is outputting sound also at 70 decibels. So the question is, if I have these two machines acting together, what is the total intensity? Or what's the total decibel level? Is another way of asking it. Is it going to be 140? Two different questions. What do you think? Is it going to be 140 decibels when you add them together? Is it going to be less? Is it going to be like, I don't know, 80 decibels? Is it going to be 60 decibels? It's definitely going to have to be bigger than 70, right? What do you all think?
I mean, I'm thinking about the example of the piano. I would assume they would probably be the same. Then they would mimic each other. So I want to say like 70.
You think it's still going to be 70? Okay. Kate says something maybe like 80 or something like that. All right, let's see what happens. So it turns out that when we're talking about decibels, we can't actually just add them because, you know, let me give you an example of that. Let's look at our list right here. So on our list, ordinary conversation right here is labeled at 65 decibels, right? So let's say you're in a room where there are two sets of people having conversations. If decibels added like that, then a group of 4 people that were each having separate conversations with 65 decibels per conversation, if you were to just simply add them, you'd get about 130, which is above the threshold of pain. And that's somewhat ridiculous, right? Just because 2 different groups of people are talking in the same room, it doesn't mean that their total loudness is going to add together exactly like that. What you have to add together is the intensity. So the first thing you have to do is you have to take 70 decibels and you need to convert that into an intensity, right? So if I say 70 decibels is equal to 10 dB multiplied by the intensity of the machine divided by our reference intensity I naught, we can find the intensity of the machine by realizing this isn't the real equation. There's a log in here too, sorry. There's a log in here. So in order to do that, what we need to do is to pull out this right here. So let's start doing that. 70 over 10 is 7. I'll just call it IM for short. Raise both powers to the 10. We get 10 to the 7 is equal to IM over I naught, which means that IM is going to be equal to the initial the reference intensity times 10 to the 7. And our reference intensity was 10 to the minus 12 watt over meter squared. You multiply that times 10 to the 7. Let's see, 7 minus 12, we get 10 to the negative 5 watts over meter squared. So this is the intensity for one machine. Now, assuming we're the same distance for both of these things, so let's say we're standing right here in the middle, and so the same distance away for both of these, because if we're closer to one of them, it's going to sound louder than the other. Right? The intensity for one machine is that. In order to find the intensity for two machines, well, intensity is power per unit area. Power is a type of energy, and energy is a scalar, so we can add intensities just like we would add mass. So for two machines, we're going to get double the intensity. So that's going to be 2 times 10 to the negative 5 watts over meter squared, right? This does add. So this is the total intensity for two machines right here. And now if I want to find the amount of decibels associated with two machines, I go back and I use my equation again, and we do log of, now in the numerator we'll put 2 times 10 to the minus 5 watts over meter squared. Divide that by 10 to the negative 12. And now we're going to get an answer. I think we're going to get 73. I'm pretty sure that when you double intensity, it increases decibel level by 3. I think we're going to be able to prove that that's true here in a second. That's my memory. It's been a while since I've done this stuff. So 2e minus 5 divided by 10, or 1e minus 12. I get, tell me if you all get the same thing, I get 7 times. That's exactly what I said, 73. So again, what were we talking about? We were saying, how intense is it if I have two machines that are 70 decibels? And the answer is, as long as I'm the same distance away from both of them, it's 3 decibels more. So if I were to add like 20 machines, right? Each machine that I add is going to increase the decibel level, I believe, by 3 decibels. So 20 machines operating at the same time would be like 20 times 3 is what? 60? That doesn't sound quite right either, does it? But the math does seem to show that that's the case. Let's see if we can prove that part. No, that's not how it works. You're right. Okay, we'll answer that question in a second, Kate. You're right. I don't think that's how it works. Let's see why it is that 3 decibels corresponds to 2 first. Okay, so what we basically said is that beta for two things is going to be 10 dB times the log of 2 multiplied by whatever... Oh boy, that was weird. It's 2 times I of the machine, right? The intensity of the machine, divided by I naught, right? And we want to see how does this compare to beta for just one machine, right? 10 dB log of I over I naught, okay? This is beta 1. So what we really want to figure out is how are these related to each other, right? And what I would say is what we can do is we can use some log properties to say this is going to be 10 decibels. This whole thing can be written as the log of 2 plus the log of I over I naught. Would you all agree? Because if I have the log of A times B, this is equal to the log of A plus B. Well, the log of A plus the log of B. So the log of 2 plus the log of S should work, right? And that means that beta 2 should be equal to 10 dB log of I over I naught plus 10 dB log 2. And this is 3, I think, right? So if I do 10 log 2, this is 3. So this thing is equal to 3 decibels. And that's why having a second machine would make it so that we were, so that we get this relationship that beta 2 is equal to beta 1 plus 3 decibels, right? Now, let's go a little bit farther, and let's say we have n machines operating. If we have n machines operating, beta sub n would be 10 decibels times the log of n machines, right, times I over I naught. But we can play the same game, and we can say beta sub n would then be 10 dB log of I over I naught plus 10 dB log n. So this is why what I said earlier was not quite correct. So what's that equal to the log of n? So let's say that we take n equal to 20, for example. So beta sub 20 would be equal to beta 1, whatever the intensity of one machine is, plus 10 dB log of 20. And then this is going to be 10 times log 20. This is 13 decibels. All right, so I was in fact incorrect. And as I was saying, it didn't make any sense. So you're correct to question that. Okay. So there we go. 13 decibels for 20 machines, yeah. So there's some, yeah. Well, anyone have any questions? We're now over time, so we'll stop there. We'll do some more problems with decibels here when we come back. And then all that's left is to talk about sound waves in tubes and pipes, interference of waves, and the Doppler effect. And we'll be done. Doppler effect is a lot of problems, so we'll be spending, I believe, quite a bit of our time next time on the Doppler effect. In fact, it may make the most sense to just start with the Doppler effect and make sure that we cover everything. You will have a homework assignment on mastering physics for this chapter. I just haven't put it up yet. I think because last time I taught this class, we didn't actually get this far. So anyway, look for that, and it'll be due at the very last day of the semester, like on Friday. But remember that we are meeting again on Wednesday night, and we'll finish up this chapter on Wednesday night. Okay, so I'll see you all then. Hope you all have a nice night, and take it easy.
Have a good night, Professor.
You too.